All right. Hey everyone. So we're gonna again continue looking at logistic regression. The bulk of this video will be just spent on what happens if or if at least one of our predictors is categorical now. And so this first little part, again, I'm in the note packet at the top of page 8 for day 21, 22, is just, well, okay, if we have more than one predictor, it's not too difficult to just expand our equations to include multiple predictors for a multiple logistic regression model. And so again, you could write in the probability form, or you could write in the logit or the log odds form. And so remember, if you're writing in the log odds or logit form, then it's linear on that scale. And so we'll see an example of using multiple predictors in the accompanying handout. For now, let's jump into, okay, well, what if we have multiple predictors, but one of those predictors is categorical? So we're sticking with our college public-private data set, and now we're thinking about adding a indicator variable as a predictor in the model. In particular, we're looking at this coast indicator, and so we're defining that so that this coast indicator is a 1 if the school is on the coast, and a 0 otherwise. And so the coast for these United States colleges means that the school could either be in a state that's on the west coast or in a state that's on the east coast. And so if we fit this model, again, we're just in the same similar type of deal that we did for LM. We could just add it as a predictor in this GLM statement in R, and we get this nice table of output. So let's go ahead and write this model in logit form. So our log odds, and then I'm just grabbing the 3 coefficient estimates from that table to get our fitted equation. Okay, so then let's see if we could interpret this coast indicator slope coefficient estimate in context of this problem. And so to do that, let's calculate a couple of odds. First, the odds of a school being public that's on the coast with a 13 student to faculty ratio, and then second, for a school not on the coast with that same ratio. And so if you do this calculation, it's super similar to how we dealt with indicator variables before, where I'm just going to plug in, if it's on the coast, then I'm plugging in a 1. And if you calculate that out, that means that the odds, kind of raising both sides to this e power, is going to be equal to this. And so that is equal to 0.036924. We could do the same type of deal for a school that's not on the coast with the same student to faculty ratio. Again, this last term is just going to drop out, but I'm plugging in the 0 just to be super clear. And so our estimated odds of a school being public for that school are 0.082546. And so from those, let's go ahead and figure out this odds ratio and then see how it relates to that estimate in our table of summary output. So our predicted odds for the coast school versus the predicted odds for a school that's not on the coast are 0.036924 divided by 0.082546, and that ratio is 0.4473. Okay, so how does that relate to like the summary output or whatever? And what we did before when we had a quantitative predictor was the first thing we did was raise that to the e, or raise that by e. So if we do that, that should be the exact same number that we got from taking this odds ratio. So what that means is, okay, then that means we estimate that the odds of a coast school being public are 0.4473 times the odds of a non-coast school being public. All right, and so now that we're in multiple regression, so that part we can't forget that was kind of implicit in us calculating this example, is that the student to faculty ratio didn't change at all. So both of these calculations were done with a 13 student to faculty ratio, so we just need to add at the end as long as student faculty ratio doesn't change. Okay, so yeah, we're kind of getting like a little bit more mathy with these past couple videos, so I think some of you will probably like that, others might not. But kind of doing this type of math, it's important that we just kind of see where this interpretation comes from and that it just doesn't just pop out of nowhere. Okay, and so this last model then, you'll notice that I'm fitting it, but now I'm including this interaction term. And so take a second to think about what this model would mean and why you might want to use it as opposed to the non-interaction term model. Okay. Oh, okay. Sorry, something made me laugh. I'll link to it in the description that made me kind of think of this. So we're thinking about this interaction model. First of all, one big point of this is just to show that so much of the stuff that we did in multiple regression also applies to logistic regression. It's not like you move to logistic regression and then all of a sudden you can't do interaction terms. They really are interpreted in a super similar way. So if we had this interaction, then that would mean that the model is going to now allow for the association between student-faculty ratio and whether or not a school is public. So this association between our quantitative predictor student-faculty ratio and our response, whether or not the school is public. So our model is going to allow for that to be different for schools on the coast and schools not on the coast. So that's like a super similar interpretation of an interaction to what we had before. This is essentially a non-parallel lines model. But remember from before that this is linear on the Logit scale. And so it's a non-parallel lines model on this Logit scale. So just like another brief note, so just to remember the probability scale doesn't have lines. So, because it's like a curve that kind of goes in the probability scale. And so that's what it's really kind of analogous to. So we'll kind of wrap up this little introduction with a couple of ways to assess overall model fit. As always, let me know if you have any questions about anything.